This is video 6-1, types of intramolecular bonds, the Octet Rule, and Lewis structures. Okay, so in this chapter we're looking at chemical bonding. Okay, chemical bonds. These are mutual electrical attractions between the nucleus and the valence electrons. Okay, the valence electrons, remember, these are the outermost electrons. Okay, these are the ones in the highest energy level. Okay. So, reason why we learned about electrons, electron arrangements, these are basically going to determine how chemical bonds are formed. Okay. So, why do bonds form? Okay. Just like anything that atoms do. Atoms are basically lazy, remember. They want to try and get to the lowest energy state possible. That makes them more stable. Okay. So, if by bonding it makes them more stable, gives them lower energy, then the atoms will rather bond than be unbonded. Okay, now, a couple different types of bonds that we can have. Ionic bonds. These are electrical attractions between ions. Okay. Metallic bonds, we'll go over this a little bit later, but these involve electrons again, but these are what are known as delocalized. Okay, and you'll learn about those when we get to that section. And covalent bonds. These basically involve a sharing of electrons. Okay, now be careful with this idea. If you go back earlier, okay, there still has to be an attraction between the nucleus and the electrons. Okay, so even though they're being shared in covalent bonds, this is not where the attractive force comes from. Okay, all of these types of bonds involve electron interaction, to some degree of sharing. The difference arises in how the electrons are going to be shared. Okay, so how do we distinguish between a covalent bond and an ionic bond? Metallic bonds should be pretty simple. It's pretty much just going to be in metals. Okay, so what we have to do is look at the electronegativity of the atoms that are involved in the bonds. Okay, and this is what you learned in the last chapter. Okay, and on page 151 from the last chapter, it gives you the electronegativities. Okay, so the differences, you look at atom X and bond it to atom Y. Okay, look up atom X and look up atom Y. Find their electronegativities and then find the difference between them. If the difference is between 0.0 and 0.3, basically it's a covalent bond and it's a nonpolar. If the difference is between 0.4 and 1.7, it's still a covalent bond, but now we call it a polar covalent bond. And if the difference is 1.8 or greater, it's basically an ionic bond. Okay, so the differences in electronegativities tells you what type of bond is going to be formed. Okay, now, what's a polar bond? Okay, this arises when the electron density, in other words, remember the orbitals where the electrons are going to be found, are not, the electron density is not evenly distributed between atom X and atom Y. Okay, so the electrons that are being shared between X and Y, they're not evenly distributed. And they're going to be held closer to the atom with the larger electronegativity. Because that's what electronegativity is. How strong the tug of war between atom X and atom Y is. They're pulling on these electrons right there. Okay, so this is a polar bond. Okay, so let's say this is hydrogen and this is chlorine. Chlorine has a lot larger electronegativity than hydrogen. So the electrons that are going to be shared in the orbital section, the overlap of the orbitals of the hydrogen and the chlorine, there's going to be a lot bigger orbital overlap, a lot bigger electron density around the chlorine. Okay, so that means there's a higher probability of you finding the shared electron closer towards the chlorine. Okay, now, these signs here, these are the lowercase, delta, Greek symbol, and this basically means partially positive, and here it means partially negative. What does partially mean? That means if it were negative, the electrons would have all jumped over towards this way. Okay, but they're still held between the hydrogen, so the hydrogen didn't lose all of the shared electron completely. So partially negative spends most of the time around here, spends not too much time around here. Okay. Now, nonpolar bonds. Basically, when the electronegativities are similar to each other, then the differences are going to be really small. Okay? So the electrons will be evenly distributed between the atoms. These are the shared electrons. Okay? So chlorine 3.0, pretty high electronegativity. But when one chlorine atom bonds to another chlorine atom, the shared electrons are pretty much evenly distributed because both of these are pulling equally on the electrons. Tug of war, nobody's winning. Okay, so that's pretty much what a nonpolar bond is. Okay, next thing we'll look at, the octet rule. Okay, octet rule says that atoms tend to form so that each atom has 8 valence electrons, hence the name octet. Okay, but the more important or more correct way would say is that they form so that they end up with a noble gas configuration. Okay. In most cases, that means most noble gases had 8 valence electrons, but in the case of helium, remember, 2 made it stable. Okay. So what does this have to do with making compounds? Well, depending on what atoms are bonding, what is X, what is Y. Okay. X can gain or lose an electron, Y could gain or lose an electron, or they both could share electrons, so that when you count the number of electrons total, hopefully they end up with an octet. Okay. Now, there are some exceptions. Okay. Hydrogen doesn't want to try and get to 8 because remember, hydrogen only has 1 valence electron. Okay. Boron basically only has 3 valence electrons. So it tries to get to 6 valence electrons after bonding. Okay, now this doesn't make it stable. Okay, hydrogen tries to get to 2. It has 1 electron. It ends up having 2 valence electrons, which pretty much makes it look like helium. Okay, so that's fine because helium is a noble gas. Now the 6 doesn't make it stable. Okay, but that's what it does. Okay, and some non-metallic elements in the 3rd row or lower, like sulfur and phosphorus, can actually make what's called expanded octets. And in this case, they actually end up with more than 8. Okay, now, Lewis dot structures, okay, or electron dot structures. Okay, basically, these show symbols for the element along with the valence electrons, any bonding electrons, and or any non-bonding electrons. Okay, and they show them as dots. Okay, so simple example: lithium. How many valence electrons? How do you figure out number of valence electrons? Simple. Valence electrons is equal to the column number. Hopefully you remember that. Okay, so lithium is in column 1. Not the atomic number, but column number. Column 1, so that means there's 1 valence electron. So that's all you do. Okay. Fluorine is in column 7. So that means it has 7 valence electrons. So you'd be going 1, 2, 3, 4, 5, 6, 7. Okay. Try not to put more than 2 electrons per side. Okay, rules for drawing Lewis structures. Okay. Any uncombined element, all you do is show the number of valence electrons. Use the periodic table, and again, you just look at the column numbers. Okay. And they do not need to follow the octet rule because the octet rule basically works for when they're making compounds. Here they're talking about pure elements. Okay. Now, when bonding, okay, H is never a central atom. Oxygen is rarely going to be in the central atom. In other words, if you wanted to figure out what's the structure of H2O, it cannot be H bonded to an H bonded to an O. Okay. Hydrogen has only 1 valence electron. This can only make 1 bond. Okay, so there's no way it can bond there and also bond there at the same time. Okay, so oxygen usually not going to be in the middle. But in this case, that's the only way it can be. So H has to be surrounding an O, and then H on the other side. Okay, now, how do you know how to put bonds? Okay, the number of electrons each atom needs to complete its octet. That's how many each atom has to share with the other atom. Okay, and we'll go over this in a second. If you have two shared electrons, which is one pair, that makes one bond. Okay, when you have two electrons being shared, we show the bond with a line. Okay, so every line means you have two electrons, two dots. Okay, unshared electrons, just because something has 6 electrons doesn't mean it's going to share all 6. Okay, any ones that are not going to be shared, do not put them between atoms that are bonding. Okay, now, how do you know when you're done? Not counting the shared electrons. Each atom should still have its correct number of valence electrons. So, if we started out with oxygen, oxygen has 6 valence electrons. When you're done, before you connect your dots and make bonds, you should still have 6 valence electrons around the oxygen. Okay. Now, every once in a while, you're going to have to do a couple weird things. Okay. Normally, atom X and atom Y are going to bond. X has to share 1 and Y has to share 1. Okay. But sometimes, one of these atoms contributes both and the other one contributes none, meaning X would actually contribute 2 electrons, Y would contribute no electrons to make a bond between X and Y. Okay, if that's the case, you end up with something known as a coordinate covalent bond. Okay, these are identical. These are still made up of 2 electrons. They're still shared. They still belong to both X and Y. Okay, and you indicate them with, instead of drawing a line, you draw them with an arrow. Okay, and it points to the one that did not donate any. No electrons are being contributed to the bond. Okay, and then X would be sharing 2 electrons. So there's still 2 electrons being shared between X and Y. Both of them come from X. Y doesn't share any. Okay, now, if you need to draw the Lewis structure for polyatomic ions, okay, the entire structure, all the atoms go inside big brackets. Okay, the charge you write as a superscript outside the bracket, so the charge would go up here. Okay, whatever the charge says to do, that's what you also have to do with the electrons. If it's negative, you're going to add electrons. If it's a positive charge, you have to remove the number of electrons the charge says. Okay, but you still follow all the rules we talked about. Okay, so some examples. Okay, and you'll get lots of practice. You have a worksheet also to work on this. Okay, so let's figure out how to draw the Lewis structure for water. Okay, H2O. First thing you have to do, figure out what is the actual arrangement of the atoms. Okay, and we said it cannot be HHO, it has HOH. Okay, refer back to this part of the video if you keep forgetting how to do it. Okay, each atom, figure out how many it has. Hydrogen has 1. Oxygen has 6. This hydrogen also has 1. So, it has 1, it's going to try to get to 2. This is also going to try to get to 2. This is going to try to get to 8. Okay, so how many does it have to share? It has to share 1. Has to share 1. From 6 to get to 8, it has to share 2. So that's how many they have to share. Okay, hydrogen has 1, so it's going to share 1 with that oxygen there. Okay, same with that hydrogen there. Okay, oxygen has 6, it has to share 2, so it'll share 1 here and 1 here. Okay, now you have to put in the rest of the remaining valence electrons. It's sharing 2, so that means you still have 4 electrons. Okay, oxygen has to have 6 electrons. 1, 2, 3, 4, 5, 6. Okay, now where they've been shared, draw a line, draw a line. Okay, Now, how do you know that you did it correctly? Simple. Count the number of electrons around each atom. Okay, so each line represents 2, so that means the hydrogen has 2. Okay, same thing there. Has a line, so that has 2. Oxygen, 1, 2, 3, 4, 5, 6. Okay, 7, 8 when you count shared. Or you can go 1, 2, 3, 4. This line counts as 2. That line counts as 2. So 2, 4, 5, 6, 7, 8. Okay. Now, is everything happy? That has 2, looks like helium. That has 8, looks like a noble gas. That has 2. Okay. So the correct structure is this. Okay. N2. This one should be simple. Nitrogen bonds to a nitrogen. Okay. Now, each one has 5. So how many should it share? Well, that needs to get to 8. That needs to get to 8. So that means it has to share 3. That has to share 3. 1, 2, 3. 1, 2, 3. Don't forget the nitrogen has to have 5. So that means 2 are going to be non-bonding. Okay. Now we got 1, 2, 3 bonds between the nitrogens. Okay. CO2. Okay. Now what's the arrangement going to be? Is it going to be COO? Okay, remember, oxygen's usually not going to be in the middle, so that's not the arrangement. It's going to be O, C, O. Okay, carbon has 4, 6, and 6. Okay, that has to share 2, has to get to 8. That has to share 2 to get to 8. This one has 4, the carbon. That means to get to 8, it has to share 4. So it has to share 2 on the left, 2 on the right. Okay. Now, oxygen has to have 6. It's sharing 2 there. So you have 1, 2, 3, 4 more that are non-bonding. Same thing here. Doesn't matter where they go, just don't put them between the ones that are being shared. Okay. Carbon has 4. 1, 2, 3, 4. No more non-bonding. Okay. So you got 1, 2 bonds, 3, 4 bonds. Okay. Now, does everything have 8? The lines count as 2 for both sides. 2, 4, 6, 8. So that's fine. 2, 4, 6, 8 for the carbon. 2, 4, 5, 6, 7, 8. Okay, so everything has an octet, so that's a good structure. Okay, HCl. H bond to the Cl. Hydrogen only has 1. That's all it can share. Chlorine has 7. Tries to get to 8, so it has to share only 1. So that means it still has to have 7, so there's 1, 2, 3, 4, 5, 6 more left over. Okay. The bond counts for 2. That's fine. Hydrogen just needs 2. 2, 4, 6, 8 for the chlorine. Okay. Polyatomic ions. NO3 1 minus and SO4 2 minus. Okay, let's do this on the next sheet. NO3 1 minus. Okay, now, since these are ions, we've got to do them in big brackets. Okay, oxygen's not going to be in the middle. So, nitrogen surrounded by oxygens. Okay, and it's a -1 charge. Okay, now, oxygens have 6. Nitrogens have 5. Okay, so, how many more they need is also what they're going to have to share. Okay, this needs 2 more, this needs 3 more. Okay. Now, don't forget though, this -1 charge means you have 1 more electron. Okay. Now, easy way to do this. Add it to the middle one. So instead of 5, we'll make that a 6. Okay, then we don't need to worry about putting it in later. So if that has 6, that means the nitrogen only needs to share 2. Okay, now we got a little problem. Okay, how do I make the nitrogen share 2 when it has to bond to 3 things? Okay, and a couple different ways you can do it, but the correct way is this. Nitrogen shares 2 with this oxygen. Okay, that means this oxygen has 1, 2, 3, 4 left over. Okay, sharing 2, you got 4 left over. That means the nitrogen should also have 4 left over. Okay, I'm going to put them here because they cannot share anymore. Okay, now 2, 4, 6, 8, 2, 4, 6, 8. Okay, now if I were to share 2 more with the bottom, nitrogen would end up with too many. Okay, if I share those 2 like that and say, okay, we'll put those away, that would mean nitrogen would have 2, 4, 5, 6, 2, 4, 6, 8, 9, 10. Okay, so we can't do that. So let's erase these. Okay, so oxygen has 8, nitrogen has 8. Now the problem is these two oxygens still haven't bonded. Okay, so what do? Well, nitrogen already has 8, so 2 of these turn into an arrow going that way. Okay, the oxygen doesn't share any, so it still has 1, 2, 3, 4, 5, 6. Okay, the other nitrogen, or the other oxygen, still has to be bonded, so the last 2 also do that. And that means this oxygen didn't share any, so it has 1, 2, 3, 4, 5, 6 still left over. Okay, so this is our structure now. Okay, everything has 8. 2, 4, 6, 8. The nitrogen has 8. There's 8. 4 lines. Okay, 2, 4, 6, 8 has 8. 2, 4, 6, non-bonding plus the line, that's 2 more, 8. Same thing with that oxygen. Everything has 8 there. Whoops. And our last one. SO4 2 minus. Okay, again, in the brackets, minus 2. Sulfur's in the middle, surrounded by oxygens. Okay. Now, sulfur, same column as oxygen, it has 6. Oops. Oxygen also has 6 valence electrons. They're both in column 6. Okay. But this minus 2 means add 2 more. So sulfur ends up with 8. Okay. That means it doesn't need to share anymore. So how's it going to bond to the oxygens? Simple. Each one of those pairs of oxygens, or pairs of electrons, there's 4 pairs, they make 4 coordinate covalent bonds. That means each oxygen doesn't share any. So each one has 6. Okay, so how do you learn this? Practice. So here's your review. How can you determine an element's valence electrons from its position on the periodic table?